Okay, good morning and welcome to this video course on advanced hydrology. Looking back in the last class, we started the new chapter on subsurface water. Okay, and I would like to go over the slides which we looked at in the last class. So, here you see initially we looked at the subsurface water, the different physical processes, how they take place in the nature here, and then we looked at a cross section through an unsaturated porous medium, where we said how the air filled voids are changing as a function of time when we increase the water. And then we defined certain properties of soil, that is porosity, and then we defined the moisture content like this equation, and then we said that the moisture content in the soil is normally between 0 and eta is the porosity. Then we derived the basic governing differential equation for the one dimensional unsteady unsaturated flow, which is called the Richards equation. It is a combination of the continuity equation and the momentum equation, where we looked at the control volume approach shown here, and then we applied the continuity and momentum equation. I will not go through this whole process again, and continuing further, this is the continuity equation, all right, equation number 6 we derived, and then we took the momentum equation in the form of this Darcy's law, all right, and then we split the head or the energy which causes the water to infiltrate into two components. We neglected the kinetic energy and we said it consists of suction head and the datum head, all right. With this we looked at the concept of the suction head here, and then we moved on to derive or combine the continuity and momentum equation to finally write the equation number 12, which is our Richards equation. Okay. Then we moved on to the concept of infiltration. We defined what is infiltration, and then we said it is the what are the factors on which the infiltration depends, and we said that it is the properties of the soil, it is the land use and land cover properties of the catchment, and also the antecedent moisture conditions or the initial conditions in the catchment. Then we looked at the moisture profile as we go below the ground, all right. This is the soil moisture profile during any rainfall event, in which we classified the ground moisture conditions into three different classes. First is the saturated, then we have the transmission zone, and then finally we have the wetting zone. And wetting front is something at which the moisture content decreases abruptly, and the wetting front is marching downwards as a function of time during a rainfall event. Then we defined what is infiltration rate and what is the cumulative infiltration, and then we said that one is the cumulative of the other, or once we know one of them, other can be calculated. With this we would like to start with slightly different concept in the form of the equations which we study, whether it is Horton equation or Holton equation or the Green-Empt equation, what does it represent, all right. So, the first concept which is very important to understand is that the most infiltration equations, do they give us the actual infiltration or the potential infiltration? Okay. I am sure you may have studied the Horton equation, all right. Now, does it give us the actual infiltration that is occurring, or it gives the potential, all right. Some of you may know this, but all these infiltration equation, it gives us, or they give us the potential infiltration, that is under any given climatic and catchment conditions, what is the maximum amount of infiltration that can occur at that given point of time. Okay. That is what any equation gives us. Then the question that arises is, how do we find the actual infiltration, all right. For example, you have Horton's equation, it gives you certain rate f is equal to 2.37, but it is not actual, it is potential. So, how do we find actual is, we compare that potential infiltration rate with the intensity of rainfall. Okay. So, if let me first define that the actual infiltration rate is equal to, let us say, F A, and define the potential infiltration as, let us say, F subscript P, and the rainfall intensity during the same time interval or at the same time is, let us say, I. Okay. Now, if we compare this I with the potential infiltration rate, we should be able to say what is the actual infiltration. Okay. How do we do that? It is a simple logical operator we can use. That is, if your rainfall intensity is greater than the potential infiltration rate, then your F actual will be equal to what? If you think about it, physically what is this equation representing is that you have rainfall occurring at a rate which is much higher than what the soil can absorb. Then what will be the infiltration? Obviously, it will be the maximum amount of rate at which the soil can absorb water. All right. So, in that case, your F actual will be nothing but the F potential. Okay. So, that is how we find in the case of when the rain is falling at a higher rate than the potential infiltration rate. How about the other case? That is to say, if I is less than the potential infiltration rate, which we have found using any of the equations, then your F actual will be equal to what? If you think about it, physically what it means, that the rain is falling at the rate which is less than the maximum rate at which soil can absorb water. So, what will be the infiltration? It will be the amount of water that is available, or the rate which is available, which is I. Okay. So, the F of A will be nothing but equal to I. So, you see that this is very important to understand. Most of the software which do rainfall runoff modeling or any computer program which you can yourself write, and we will look at one of the algorithms we will develop. We use this concepts where we use the infiltration equation, calculate the infiltration rate which is the potential infiltration rate, and we compare it with the intensity of rainfall to calculate the actual. Moving further, now we look at a few empirical equations of infiltration or estimating infiltration, and first one of them we will look at what is called the Horton's infiltration equation. Okay. I am sure many of you would have seen this already in your undergraduate classes. So, it will be a slides review. Okay. So, it was first proposed in 1933 and then later on modified in 1939. Okay. As per this equation, the infiltration at any point of time, now remember this is potential, okay, but we are not using the subscript P here. Okay. So, F at any given point of time will be equal to F c plus F o minus F c times E minus k t. Okay. And I am going to number this equation as 3, where F t is the infiltration rate at any time t. Okay. What is F c? It is the long term or steady state constant infiltration rate. Okay. After a very long time, the rate of infiltration will stabilize to this value F c. F o is what is called the initial infiltration rate. That is, when the rainfall starts, it is the initial, it basically represents the initial conditions in the catchment. Okay. So, F o is the initial infiltration rate and K is defined as the exponential decay constant. Okay. The exponential decay constant will have units of time inverse, okay, because you have e to the power minus k t and this should be constant. So, we are multiplying by time. So, the k has units of time inverse. Okay. Now, certain researchers have shown, for example, Eagleson in 1970 and Rautkivi in 1979. They have shown that the Horton's equation can be derived from, as I said earlier, the Richards equation, which we looked at in the last class, under the assumption or by assuming K and D, that is your properties of the soil, all right, them to be constant. Or independent of the moisture content or time, independent of theta. Okay. So, in that case, if you look at your Richards equation, that will reduce to the form del theta over del t is equal to d del 2 theta over del x or del z square. Okay. Let us say this is equation number 4. So, if you solve this equation to get Horton equation, it should be easy to verify. We will not do that here, okay, because it is out of the scope of this course. So, what we are saying is that the Horton equation which we just saw or you have seen earlier can be derived under certain assumptions from the Richards equation. Okay. So, we will stop at that as far as the Horton equation is concerned, and we will move to the next empirical equation or next concept or method of calculating infiltration, which is called the Phillips equation. Okay. The major difference between Phillips equation and the Horton equation is that the Phillips equation assumes K and D to be your function of theta. Okay. So, they assume that the hydraulic conductivity and the soil water diffusivity D vary as a function of time as the soil moisture content varies during a rainfall event. So, once we do that, we can derive the equation or expression for the cumulative infiltration as a function of time in terms of various parameters. Okay. We are not going to do that. I will give you the final result, which is the famous Phillips equation. It comes out as ST half plus KT. Okay. And let us name this as number 5. In this equation, S is a parameter, model parameter called sorptivity. Okay, which is the function of the soil suction as the name suggests. Okay. So, S is a parameter or the property of the soil that determines the diffusivity or the suction or responsible for accounting for the suction forces. Okay. And K is obviously, as you know, is the hydraulic conductivity. So, you see that this cumulative infiltration is sum of two components. One is taking care of the suction forces and other is the gravity forces. Okay. Using this equation, we can differentiate it with respect to time and then determine what will be the infiltration rate. Okay. Once we have the capital F, we can always find out what will be the small f. So, you can see that it will be equal to half ST minus half plus K. Okay. You differentiate 5 with respect to time, you will get this. Okay. Now, it is easy to see that as time approaches very large or tends to infinity, what will happen to f of t. If you look at equation number 6, as the time becomes very large or tends towards infinity, what happens to the infiltration rate. Okay. You can see that will approach the hydraulic conductivity, that is your long term steady state infiltration rate. All right. So, as per this equation, after a very long time only the gravity forces are predominant, right. So, the Phillips equation is a very nice equation because it is accounting for the suction forces as well as the gravity forces. All right. Initially suction forces are higher, so the first component will dominate and later on the second component will. One important aspect which is important about the Phillips equation is that it can be used for horizontal infiltration. That is to say, it can be used for horizontal flow or infiltration. In which you account for only the suction forces. Let us say you have a tube and you have a container containing water on one side, then how the water will get sucked into the soil sample or into the soil in only one direction, which is horizontal or perpendicular to the gravity flow. So, we can use this equation in which we just take care of the first component and we disregard the second. So, this capital F will be nothing but ST half. Okay. So, we can use this Phillips equation for horizontal flow kind of situation. Okay. So, these are the two basic empirical equations which are used. The next we are going to look at is something extremely important, okay, which is called the Greenamp method. Okay. Greenamp method or Greenamp equations is, as I said, is very useful and very important. It is widely accepted and widely used in fact in many of the software to calculate infiltration. Why? Because it has conceptual basis. Okay. So, it provides exact analytical solution with certain simplifications or approximations. To the flow situation and your results equation. Okay. So, what we are going to do next is I am going to look at the schematic of the soil moisture profile which is used in the Greenamp equation to derive the final equations which can be used for calculating the infiltration. Okay. So, I am going to use the board. So, you come along with me and then we are going to look at the soil moisture profile which is a simplified one. That is H naught, it is the depth of the water on the ground. All right. This we are looking at is the ground level. Okay. This is the soil moisture profile. Okay. And this is the initial or residual moisture content. So, we are going to define everything here. This is called the wetted zone of hydraulic conductivity K. Okay. Let us say this is my y direction or the vertical direction and this is your x direction on which you are plotting the moisture content. On the x direction you have the moisture content. Okay. What is happening is this wetting front is continuously moving down into the ground. Okay. This is what is called theta r, or the residual moisture content. This is called theta e, and I am going to define all those things in a second. And this is the maximum moisture content in the soil, which, as we have said already, is equal to the porosity of the soil, or eta. Okay. What is this? This is your theta I. So, initially this was the initial moisture content in the soil, but due to the rainfall we have some ponding depth here H naught, and because of that we have saturated conditions close to the ground. All right, and this is a snapshot at any given time t. All right. So, what is happening is, at this time, this is the depth of the wetting front, and this wetting front will be marching down as a function of time. So, let us say at this any point of time, this length is L. Okay. So, L is the length of the or the depth of the wetting front at any given point of time. So, let me define all these variables first. So, you have theta I is the moisture content, below the wetting front, or the initial condition basically. Eta is the porosity of the soil, or the maximum moisture content in the soil. L is the depth of penetration of the wetting front in or at time t since the infiltration has started. This is important. Okay. Since infiltration started, that is to say, when the infiltration starts, the length is 0, all right, and in time t the length is L. Okay. So, all the moisture content in this snapshot will represent the infiltrated water. Okay. We will come to that little later. H naught, let us say, is the ponding depth, or the depth of water which has ponded due to rainfall at the soil surface or on the ground. Let us assume that K is the hydraulic conductivity. We have said that K is the hydraulic conductivity of the soil, and theta R is the residual moisture content. Residual moisture content of the soil after it has been thoroughly drained. Okay. So, I am sure you understand what do we mean by this concept of residual content, in which if we take a sample which is moist and we start draining it, all right, we just leave it, what will happen is most of the water will run out, but some water will be held back, which is called the residual moisture content. Okay. And different soils will have different type of residual moisture content. So, it is a property of the soil. Okay. We define what is theta E actually. Theta is the effective porosity. What is effective porosity? Is the porosity which is available for water to get or use the space, all right. So, this is nothing but the total porosity minus the space which is not available for water to fill in the soil, all right. So, the effective porosity will be equal to the porosity and you subtract the moisture content, okay. So, now what we are going to do is we will take a control volume within this depth of infiltrated water. We will use the control volume approach and try to derive what will be the expression for the infiltrated water, okay. So, we will move to our soft board here. So, we will derive the Green-Amt equation as a combination of continuity equation plus the momentum equation, okay. And what we have done is we have seen the simplified version of the soil moisture profile. So, using that with those definitions, we will write the continuity and momentum equation and we will combine those two and derive the final form of the Green-Amt equations, okay. So, what we do is, let us say we take first we derive the continuity or write the continuity equation, okay. So, for that what we do is we consider a vertical column of soil of unit horizontal cross sectional area. Okay. So, within that framework which we have just seen, let us take that we have a cylinder, okay. So, this is your depth h naught, okay, and this obviously as you see is the ground level, okay. Here we have the depth of the wetting front, okay. So, this is your L, okay. So, in the figure on the board we are taking this cylindrical column within that length L, okay, and this is marching downwards, okay. So, everything above the wetting front is the wet soil, okay. This is your ground and this is your dry soil, okay. And what is this is? This is your wetting front, okay. And we have taken a cross sectional area of this cylinder as 1 square units or square meters or square kilometers or whatever, okay. So, with this framework in mind, we will try to write the continuity equation, okay. So, what we do then is we consider our control volume as equivalent to the cylinder which we have just shown on the right of length L, okay. Let theta I is the initial moisture content in it, and we have defined eta as the porosity, okay, and theta is the moisture content at any time, and we know that theta will vary between initial moisture content in this case, which is theta I, and eta, okay. So, with this schematic in mind, let us try to write down what will be the amount of water which is stored in the CV or in your cylinder due to infiltration at any time t. Can you think about that? What will be the amount of water stored in that cylinder which we have just drawn at any given time t? Okay. Remember, we have defined L as the length of the wetting front, okay, and wetting front represents what? It represents the infiltrated water at any given time, alright. So, the amount of water stored, as you can see, will be equal to what? Will be equal to the length itself and multiplied by the area square units, alright. So, this is the volume of the CV, this is the volume of your cylinder or the CV, L times the cross sectional area, okay. That is the total volume. And how much water is there in this cylinder? What is the moisture content? It is the maximum one, which is eta minus theta I, okay. Theta I was initially already there, okay. So, the initial moisture conditions were theta I, alright. They have gone up to eta or the maximum one due to infiltration, alright. So, the amount of infiltration then is equal to eta minus theta I times the volume, okay. So, if that is clear, then we can write what will this be equal to? This is your nothing but your cumulative infiltration at any given time, and that will be L times eta minus theta I, okay, and this is represented as L times delta theta, okay. So, this is my continuity equation, okay. I have used just the first principles, okay, where delta theta has been defined as eta minus theta I. It is a quantity which is the representing the infiltration, okay. It is the amount of soil moisture content in excess of the initial moisture content, that is what basically delta theta is. So, this is your, this equation 1 represents your continuity equation. Now, let us move on and try to write what will be the momentum equation for this, and then we can combine the two. Okay. As we have seen earlier in the case of channel flow in the last couple of classes, and also we have looked at the groundwater flow situation, the Darcy's law represents nothing but the momentum equation, okay. So, in this case you have Q is equal to minus K del H over del Z, that is your Darcy's law, okay. Q is equal to KSF, or K is the hydraulic conductivity and del H del X is negative here. So, we have put a negative sign here. Now, since your Q is positive upwards and it is negative downwards, alright. So, in the present case the water is going down, or the infiltration rate of infiltration then will be equal to minus Q, okay, the Darcy's flux, alright. So, with this we can write your small f, that is your this will be equal minus will be taken care of, and it will be equal to del H del Z, and let me write it this as H1 minus H2 over Z1 minus Z2, okay. That is the first derivative del H del Z. Now, what we will do is, let me go back to my previous slide. This is your cross section 1 and this is your cross section 2. So, what we will do is, we will write the del H del Z term between these two cross sections 1 and 2, okay. So, what will be at 1, for example, what is H1? H1 is the head or energy which is causing the flow is H naught, okay. On the ground at 1 you have H naught or the depth of water, which is the energy. What is Z1? Let us say Z1 is 0, okay. That is our origin. At the ground we have datum, let us say datum is at the ground. So, Z1 will be equal to 0, okay. Now, at the cross section 2, what is H2? This is going to be very important to understand. So, let me go back. Okay. So, at this 2, this is your direction, all right. So, this is your datum here. Now, what is the energy which is causing the water to infiltrate between this length L? Okay. So, there is infiltration is due to two forces, as we know. One is the suction head and other is the gravity head, all right. So, water is getting sucked into the soil due to the suction forces, and let us say the suction head is psi, and it is because of the datum head which has a length of L, all right. And our notations are such that our positive direction is upwards. So, your H2 then is equal to minus psi minus L. Okay. I would like to request you to try to understand this very carefully. Okay. H2 is the energy which is causing the water to flow at cross section 2. Okay. And then what will be Z2? Z2 is nothing but only the datum head at cross section 2, which is minus L. Okay. So, what we do is we are going to plug these values of H1, H2, Z1, Z2 back into this equation, all of this. Okay. What do we get is your infiltration rate F is equal to K times H1, which is H0, minus H2, which is minus psi minus L. Okay. Whole thing divided by Z1 minus Z2, all right. Z1 minus Z2 will be nothing but 0 minus minus L, okay. That is Z1 and Z2. Okay. Now, what we do is we assume or assuming the ponded depth H naught to be negligible. Okay. As you know, as engineers, we always try to simplify our life. As compared to this psi and L, which may be of the order of a few meters, all right. Then H naught is a very small ponded depth on the ground, which is less than an inch or maybe a few millimeters. We can neglect it. So, if we neglect this into this equation, the final form what we get will be equal to K times psi plus L over L. Okay. So, this is your equation number 4, which relates the rate of infiltration as per the Green-Empt simplifications with the hydraulic conductivity, the suction head and the length of the wetting front. Now, what we do is by continuity. So, this equation is what? It is nothing but your momentum equation. Now, what we do is we combine this momentum equation with the continuity equation. So, by the continuity, what we have is, remember it was F is equal to L times delta theta, right, or we say L is equal to F over delta theta, okay, and H naught we have taken as 0. So, we put this into equation number 4. Okay. So, what we are going to get then is your F is equal to K times psi delta theta plus F over capital F. It should be easy to see that. Now, what we do is we say that this small f is nothing but df over dt. Now, what we do is a separation of variables. So, we combine capital F terms on the left hand side, okay. So, it will be this. So, this df with the f terms we take on the other side, this is equal to k dt. Now, what we do slight algebraic manipulations, we take it on the other side. df will be equal to k dt. So, all we have done is you have added psi delta theta and subtracted psi delta theta. Moving on further, you will have minus psi delta theta times df. We are just simplifying this equation a little bit, is equal to k dt. It should be easy to see that. Now, what we do is we integrate on both sides. One is with respect to f and other is with respect to time. Okay. If we did that, we will have 0 to f t between 0 and t, all right. So, on the left hand side the limits will be 0 to f, and what we have is 1 minus psi delta theta over this df is equal to, the limit would be between 0 and t of your k dt. Okay. After integration and putting the limits, you can do that. It will be f t minus psi delta theta, and this is the natural log of 1 over x will be equal to 1 plus f of t over psi delta theta. Okay. You integrate this quantity, all right, that is what you will get. Okay. And on the right hand side, it is k is constant, so it will be k t minus k times 0, so it will be k t. Okay. So, this is your, let us say, equation number 6, and this is your Green-Ampt equation. The Green-Ampt equation for cumulative infiltration. Okay. Now, once this capital F is found, we can always find the small f by the equation which we have already written. So, it will be k times of your psi delta theta over f of t plus 1. Okay. This equation we had already written. So, there is a relation between the infiltration rate small f and the cumulative infiltration capital F, and capital F we can find out using this equation number 6, and let me name this as number 7. In case this H naught which we have neglected, we cannot neglect it if it is significant. All we need to do then is, so let me say that if H naught is not negligible, then what we do is we use psi minus H naught for psi in these equations. So, that is the only change that is going to take place. You can verify that. Okay. Now, this equation number 6 which we have just seen or derived, there is capital F, it appears on both the sides and it is non-linear in nature. So, it is a non-linear implicit equation which is not easy to solve, all right. So, equation 6 is non-linear and implicit, all right. So, some iterative procedure has to be used to solve it. Okay. So, this iterative procedure can be either a manual trial and error or the Newton-Raphson or the successive approximation, any kind of iterative method needs to be used. Okay. With this, I would like to move on and define another important concept. Sometimes in terms of the certain parameters of this Green-Ampt equation, we call it effective saturation. Okay. And this effective saturation is defined or not denoted rather as SE. Okay. This is defined as the ratio of the available moisture divided by the maximum possible available moisture. in the soil. Okay. So, what is this then? What is the available moisture in the soil at any given point of time? Theta is the moisture content at any point of time, and available is, we subtract the theta r. Okay. And maximum possible is nothing but then maximum is eta minus theta r. Okay. So, but eta minus theta r we have defined as the effective porosity, right. It is, let us say, theta e. Okay. So, when your theta varies between theta r and eta, what will be the limits of your SE? Okay. If you look at the definition of the effective saturation SE, when theta is equal to theta r, that is the lower limit of the moisture content, then if you put theta is equal to theta r here, you can see that your SE will be equal to what? It will be 0. Okay. Similarly, when theta is equal to eta, all right, that is this one, all right, then your SE will be equal to what? It will be equal to 1.0. It should be very easy to see. Okay. So, we have this important equation which relates the effective saturation with the moisture content at any given point of time. Okay. Now, what we do is, we will write this effective saturation for initial condition. That is when theta is equal to theta I. So, what we have is, initially theta I minus theta r will then be equal to SE times theta E. Do you see that? How is this equation coming? From the definition of SE, it is theta minus theta r over eta minus theta r. Okay. In this, we put theta is equal to theta I, and this whole thing is effective porosity. Okay. And from here, that is where I have come. All right. So, that is your theta I minus theta r, that is the numerator here, will be equal to SE times theta E. Okay. Good. And let me name this this equation as equation number 9. Okay. So, now what will be the delta theta, right, which is one of the parameters of the Green-Ampt equation. So, this will be equal to eta minus, that is what we have defined initially. Okay. This is equal to theta r minus theta E, which is eta, okay, minus what is theta I? From this equation, theta I is equal to, if you can take this on the other side, that is what we will have, theta r plus SE times theta E. Okay. So, all I am doing is I am putting theta I from this equation here, and eta from the basic definition, it is the sum of the effective porosity and the residual moisture content. Okay. So, from this your theta r will get cancelled out, and finally, what you will have is your delta theta is equal to 1 minus SE times theta E. This is an important relation, okay, because delta theta is the initial moisture conditions for any type of soil. We need to know that for calculating the infiltration. Okay. Now, the last thing today we are going to look at is on the Green-Ampt parameters. We have seen the derivation of the Green-Ampt equation, and it involves certain parameters that we need to know before we can calculate infiltration. Okay. For applying any model, as you know, we need to do the model calibration. Similarly, we need to find out what is the infiltration parameters or the Green-Amp parameters for using this. As you can see, the GA parameters are what are those? Hydraulic conductivity is what we need to know for that soil. The porosity is what we need to know. Also the suction head psi for that particular type of soil, and also the initial conditions. Okay. So, for a particular type of storm or a particular situation, theta I, or in other words your SE for initial conditions is what we need to know. Okay. Normally this psi is function of the moisture content. Okay. Most of these parameters are, we consider them as constant. Let me write that first. We consider them as constants. That is to say, their values are not changing as a function of time during a rainfall event. Okay. What is a constant? Which does not change with time as far as these parameters are concerned. However, we know that the suction head and the hydraulic conductivity, these parameters can change as a function of time. Okay. So, this psi is equal to function of theta, and what many people have done is they have tried to work on this relationship, and one of them is Brooks and Corey. In 1964, they showed that these both psi and k can be derived as the function of the soil moisture content. Okay. And they gave an equation which will be used for calculating their values as a function of time or as a function of theta. All right. So, psi as well as k. Okay. I am running out of time today. So, what we will do is we will come back and look at these Green-Amp parameters and the equation which is given by Brooks and Corey, how we can represent these two parameters as a function of theta.